Hey, this is Math 8, Unit 7, Lesson 13, talking today about the definition of scientific notation. So we're going to use scientific notation, right, to describe large and small numbers. So first off, we begin today with just some numbers here, expressions, and they want us to find each expression mentally, meaning just to do some mental math and figure out what this could be. So I'm going to write it out because that way I can talk through what I'm seeing in my head, right? So here I have 123 times 10,000. So mentally what I do is I think that I'm going to have 123 and I'm going to add that many zeros behind the 1, 2, 3. So it's 4 zeros there. So I go 1, 2, 3, 4. And I can come back and put my commas in there for 1,230,000, something along those lines. The same is true here, right? Except that now I have a decimal point right there. What that decimal tells me is that essentially, instead of adding 3 zeros, I'm going to go ahead and take away one of those zeros right there. So I can put my 3, I can put my 4, and to move the decimal over 1, I eliminate a 0, so I'll add 2 zeros right there. Okay? Same idea here. If I move the decimal over there, one spot there, I eliminate one of the zeros. So I'll take the 6 and put 1 0 there. And then over here, this one's a little different because I'm dealing with a number less than 0 here, right? This is 1/100th is what this is here. If I'm going to move this one space to the right, then what's going to happen here is everything has to move an additional space to the right this way as well. So I'm going to do 73, but what happens is that instead of having 1 0, I'm going to add another 0 there to make it a little bit smaller, to make it 73. In this case here we have tenths, hundredths, thousandths, 10,000ths. So 73 10,000ths there. Alright, just some mental math for how you might work that out. So let's take a look here at the science of scientific notation. The table here shows the speed of light or electricity through different materials. We've seen this before. Circle the speeds that are written in what's called scientific notation, and then write the others using scientific notation. So to do this, we need to define what scientific notation is going to be. So here's our definition of scientific notation. Okay, scientific notation is we would say this, we would say a number is in, or written in, scientific notation when it is written as a product of two factors. Okay, that's the first part there. And within that, the first number has to be greater than or equal to 1 and less than 10. And then the second number is an integer power of 10. Okay, and then in this case here, just as a note, we use the time symbol for multiplication. Alright, so that's our definition there. So it's going to look something like this. Let's see if we can figure this out. It's when you have a product of two factors. So I have something like 2, number 2, times, using the multiplication there, the number has to be greater than 1, and then a factor, an integer power of 10, 10 to the second. That'd be an example of scientific notation. The first digit is something greater than or equal to 1. The second is an integer power of 10, and then I use the multiplication symbol there to join it together. So this is the product. Product means multiply of two factors. So I look at these choices here. The one that has a product of two factors, I know this is the product, yes, yes, and yes. Those are products of two factors there. But it has to follow our rules. The first number has to be greater than 1 and less than 10. So we see this is true there. We can see this one is not true, right? So that's not going to work. It's too big. It's true there. This is less than 1, so not true there. So far we're looking at this being a possibility and this being a possibility. Looking at the second number, it needs to be an integer power of 10, which is just 10 to the 8th, 10 to the 8th. So these two are already written in scientific notation. Now, to write the others in scientific notation, we'd have to change some things around. Okay? So when we take a look at this one right here, this number we know is 300 million. So if we want to rewrite that one, I'm going to write over the side here. I have the number 3, keeping that right there. That's going to be times 10 to the, and I have 3, 6, 7, 8 zeros there. So that's written as in scientific notation when I write it like that. For this next one, I don't want to write 28 because the number has to be between 1 and 10. So I'm going to go ahead and write 2.8. Okay, oops, put that right here, 2.8. Looking at this one here. Now if I'm putting the decimal there, then what's my value of 10 going to be? Alright, that's going to tell me how many spaces over to the left I go before I put in that, that point. Okay, so we have 3, and we have 6, 7, and 8, so we say to the 8th power again. Alright, on this one here, we have 124. Again, we want to put the decimal point there at 1.24. Now by doing that, because I moved it to the left 2 times, that's going to increase my exponent 2 times as well. So 6 plus 2 is 8, so I end up with 1.24 times 10 to the 8th. And over here, since I'm going to move the decimal over to the right, then the exponent's going to come down. So that becomes 2 times 10 to the 8th power there. So now everything in this case is now written as a scientific notation. It's written in scientific notation, and everything is to 10 to the 8th power. That's what we're going to see right there. And so now what we can look on the next page is these same numbers then. I'm going to go ahead and just use my notes here. Show up on a table looking like this. Okay? And so what we see is we see once again that our space is 3 times 10 to the 8th is over here. There's space. We can see the copper wire is 2.8, which is going to be located here, times 10 to the 8th. We can see that our ice is still 2.3 times 10 to the 8th. Water is sitting here at 2.25 times 10 to the 8th. Olive oil is 2 times 10 to the 8th. Right? And then our diamond is over here by itself at 1.24 times 10 to the 8th. And so you can see how those same numbers in their scientific notation can be written on a little chart like this to make that work. Okay? Kind of cool. So the next activity really is for you to do with a partner, and it says here your teacher's going to give you some set of cards. The cards show different numbers in scientific notation and other cards that are not. So you want to take the cards down, shuffle them up, and lay them face down, and take turns trying to match the cards with the same value. So really it's just a great activity where you're going to try to make a match. For example, you might have a number like 3 million, right, on one card, and another card you're looking for the match. In scientific notation, we'd write that as 3 times 10 to the 6th power. So when you find the match, then you're a winner. Okay? So try to go ahead and do that with your partner, and you can read the rest of the rules there and work that out with your teacher. Okay, so now I'm going to turn my page real quick there, make a couple notes here before we jump into tonight's homework. Okay, so here's a couple rules to remember as we go into tonight's homework, because these things show up in your homework as you do independent practice. Let's say that I have 3 times 10 to the 4th, and I'm going to add that to 4 times 10 to the 4th. Okay, so because my integers for the base 10 here are the same, because these are the same, I'm going to go ahead and keep that part the same, and I'm going to actually take the 3 and the 4, and because it says add, I'm going to go ahead and add that up. So this becomes 7 times 10 to the fourth. So when I'm adding up two different numbers of scientific notation and they have the same base there, we just keep the base the same and we add the numbers out in front. Okay, so that's one rule. If I'm going to take a number in scientific notation, 3 times 10 to the fourth, and I'm going to multiply it by a number, okay, what's multiplied is just the front number there. That's what's multiplied. The base stays the same. So 3 times 2 is 6, and I keep the 10 to the fourth as it is. Okay, so that becomes 6 times 10 to the fourth. Got that? All right, another example real quick. Maybe you have 3 times 10 to the fourth, and then we're going to square that. Okay, from squaring it, that's like saying what? It's like saying 3 times 10 to the fourth times 3 times 10 to the fourth. When you do that, what's going to take place is you're going to multiply those together. And these ones here, when you multiply things of the same base, what do we do to the exponents? We're going to add the exponents. So we add the exponents here, and then we're going to multiply these. So 3 times 3 is 9, and then for the exponents it's 10 to the 4 plus 4 is 8. And that's what we get there. These are just samples, just want you to have, so when you go to your homework you have some examples here. The next one here, again, if you have 3 times 10 to the fourth times 2 times 10 to the fourth, again we just did one just like this a second ago. What are we going to do? We're going to multiply those together, so 3 times 2 is 6, and this part here we're going to add the exponents, so 4 plus 4 is 8. Alright, so there's that one. And let's do one final one here. Let's do a 3 times 10 to the fourth, like this, and then a 5 times 10 to the fourth. Again, same idea. 3 times 5 is 15, and then when we put those together we end up with 10 to the 8th power. Alright, so just some samples there to help you out before we jump into tonight's homework. Okay, so again, as let's look here, we have Are You Ready for More? So a couple we'll do real quick. So what is 9 times 10 to the negative 1 plus 9 times 10 to the negative 2? Okay, so 9 times 10 to the negative 1. 10 to the negative 1 is 1/10 as a fraction, and 10 to the negative 2 is 1/100th. So you're talking about 9 times that, or you're talking about 9/10 plus 9/100ths. So thinking about that as a decimal, that's going to be, here's 0. So in the 10th place we put a 9, and in the 100th place we put a 9, so you get 0.99. Okay? As a fraction, that would be 99 over 100. Just like that. Okay? And that's how that works. So let's look at the next one. Here you have 9 times 10 to the negative 1, negative 2, negative 3, negative 4. So again, what we're talking about here is this is 9/10ths, this is 9/100ths, 9/1000ths, and 9/10,000ths. Why? Because it's 4 behind the decimal. 1, 2, 3, 4. So it looks like that. So we have, as a fraction, we have 999, and what place value am I in? I'm in the 10,000ths place value, right there. Okay, and that's the idea. And again, if you did a long way, you could do it the same way. This is 0.9 plus, this is 9/100ths, so we have 0.09 plus 0.009 plus 0.0009. When you add all that up, it still makes that right there. Okay? The answer to the two previous questions should have been close to 1, which is pretty true. That's pretty close to 1, and that's still pretty close to 1. What power of 10 would you have to go up to if you wanted your answer to be so close to 1 that it is only 1/1,000,000th off? Okay, so you're talking about doing, if your bottom number is 1/1,000,000th, okay, 1/1,000,000th, that means that our bottom number needs to be, you have 6 zeros in it. So it's going to be 10 to the negative 6 power, right? So here our largest was 10 to the negative 4th. That's how we got there. So to make it 1/1,000,000th, we're going to do 10 to the negative 6th. Okay? What power of 10 would you have to go up to if you wanted your answer to be so close to 1 that it was only 1/1000,000th off? Well, again, that's billionth, we're going to have 369. We're talking about, in this case here, doing 10 to the negative 9th. Can you keep adding numbers in this pattern to get as close to 1 as you want? Yes, you certainly could. And you could have 10 to the negative, 99th, It's just going to get larger and larger, but you're getting closer and closer to 1, but you'll actually never, ever get there because there's always a little bit of space, which is what number 5 is really asking about, if it's ever possible to get there. So in summary for today's lesson here, it says a total value. Well, I'll give you some examples here. And scientific notation really allows us to write these numbers in a certain way. We can take a number like 400 million, and instead of writing out as 400 million like so, we can recognize that I can take that initial digit and put it here in front, and it has to be greater than or equal to 1, but it needs to be less than 10, so that follows a pattern. It's a product of two numbers, so we're going to multiply it out, and I have an integer with a base 10 value here. It tells me 10 to the 8th power, which in this case here says I have 8 zeros, or I have 8 spaces behind the decimal, and that works out there. Again, we use the X symbol, multiplication symbol, for the standard way to show multiplication, and that's what we do there all the time. Okay, so just some great examples of what we did there. So remember, just as a rule, the first factor is a number greater than or equal to 1 but less than 10. The second factor is an integer power of 10. So it has to have that in order to be something in scientific notation. So let's pause there and take a moment to do our homework, and then we'll check this out together. Alright, so here's our homework for tonight. Write each number in scientific notation. Okay, so I want to put a break right here, right? That's my break's going to be. So I'm going to do 1.47. And how many spaces are going to be between the break and the initial decimal point? 1, 2, 3, 4. So it becomes 1.47 times 10 to the 4th power. Alright, in this one, we're going to go ahead and put our break right here between the 8 and 3. So we have 8.3 times 10 to the, and because we're going less than 1, we're going to take a look and see, well, how many spaces are between the decimal and our break. We have 1, 2, 3, 4, so it's 10 to the negative 4th power right there. Here, we're going to break it there between 7 and 6. We'll do 7.6 times 10 to the, and how many spaces here? 3, 6, 7, 8. So the 8th power. Okay, next one, we're going to break it between the 3 and the 8. So the 3.8. And multiply that by 10 to the negative. How many spaces are here? 1, 2. Okay. Here, we're going to break it right there. So we'll do 3.8 again. But how many spaces we have there? Just the 1. So it's 10 to the negative 1. And in this case, we already have 3.8. So we're good there. But what do I multiply the 10 by? Well, I don't want to change. If I multiplied it by 10 to the 1st power, I'd end up with 38. I don't want that. I want to keep this exactly like it is. So if I multiply it by 10 to the 0 power, what 10 to the 0 power is? 10 to the 0 power equals 1. And 1 times 3.8 is still 3.8. For G, we're going to break it right there again. So there's 3.8. I'm going to multiply how many digits are here. So you have 3, 6, 9, and 12. So So that's 10 to the 12th power. And finally, our last one, we have just the 9, and we're going to break it there, which is fine. So we have 9 times 10 to the negative. We got to count these up. We have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So 9 times 10 to the negative 10th power, and we're set. All right, number 2. You have to use those extra notes we made today. So here we go. Perform the following calculations and write them in scientific notation. Okay, so in this case here, because I am just adding things up and I'm using addition, my base 10s are going to stay exactly the same. So I'm going to have times 10 to the 5th, no problem. And then I'm going to go ahead and add those two numbers together. And 2 plus 6 is 8. That's our first one. On this one, I'm going to go ahead and distribute the 2 to the front number right there. So 4.1 times 2 is 8.2. And I just leave the base 10 exactly the same, leave it alone. And I'm okay, that's less than 10, so it's still just fine. Here, same idea, we're going to multiply this out. So 3 times 1.45 is going to be 4.5. And again, the base here, 10, stays exactly the same. In choice D, I'm going to square this one. So 3 squared becomes 3 squared, which becomes 9. That equals 9. And here, I'm going to multiply those together. So that becomes 10 to the 3 times 2, which is 10 to the 6. So let's put that together, and what do I have? I have 9 times 10 to the 6th power. And for our last one, the bases here are the same, but I'm multiplying now. So what we're going to do is we're going to multiply this. So 9 times 3 is 27. I'm going to multiply that by, when I multiply things with the same bases, then I add the exponents. So 10 to the 6 times plus 10 to the 6 times 10 to the 6, 6 plus 6 is 12. I can't leave it there, that's not scientific notation because I have 27, it's greater than 10. So I'm going to move the decimal to the left. When I move it to the left, then my 10s is going to become one more, so I get 10 to the 13th. And there we are. Alright. Jade is making a scale model of the solar system. The distance from Earth to the Moon is about 2.389 times 10 to the 5th miles. The distance from the Earth to the Sun is about 9.2 times 10 to the 7th miles. She decides to put Earth on one corner of her dresser and the Moon on another corner, about a foot away. Where should she put the Sun? Okay, so here's what she has. She has her dresser. Let's just draw the top of that here, something like this. And she puts the Earth here, and maybe the Moon's going to be over here. And the distance from here to here is about 1 foot. Alright, and that 1 foot represents, in this case here, 2.389 times 10 to the 5th. Okay, now she wants to know where she should put the Sun at, because the Sun's going to be way out here somewhere, and it's going to be 9.296 times 10 to the 7th. That's where the Sun's going to be, way out there. Right? Here's our Sun. Okay, so where should she put the Sun at? So, if 1 foot gets us 2.389, okay, times 10 to the 5th, and the Sun's going to be way out there, we have to figure, well, how far away is that going to be? Now, on your answer choices, on your book, you'll see you have a couple options here. First of all, notice that this is quite a distance, isn't it? Okay, from what it was before. If I want to think about this as being in the same base 10, I could do that by, if I want to make this a little bit smaller, to make this smaller to go down, I'll move the decimal place to the right. So I want to drop this down to 10 to the 5th, which means move the decimal 2 places. So I'm going to put 929.6. Now I know that's not in scientific notation, that's okay, but I'm using it so I can compare now. I have a 2 over here, and a 929 over there, right? So comparatively, 2 goes into 929. Well, it goes in there about 4 times. It goes in there about 3 times. Oops, sorry. It goes in there 1 time, sorry. 1, 2, sorry, it goes in 12. So it goes in there 6 times. Sorry, that's 12. And then it goes into 9 about 4 times. So it's about 464, in this case here. If this is 1 foot, this is 464 times the difference there. It's about 464 feet away, comparatively. If 1 foot is 2.3, and this is 929, that'd make it about 464 feet away. Looking at your choices here, is the window in your room 464 feet away? No, that's probably about 10 feet. Okay, the kitchen down the hallway, probably at the most, you might be maybe 40 feet, but even that's probably pushing it. A city block away, that 450 feet, or like we just did here, 464 feet, that's probably the best answer there, in terms of saying about how much farther away the sun should be in her little diagram. Alright, and let's look at this one here. It says here's a graph for one equation in a system of inequalities. Write a second equation for the system so that it has infinitely many solutions. Okay, so write a second equation for the system so that it has infinitely many solutions. Alright, so that's the graph. The equation for this graph could be something like y equals, and let's see what's happening. We're going to be going up 1, 2, 3, and over 2. We went up 1, 2, 3, and over 2. So plus 3, plus 2. So our slope would be 3 over 2, x. And then I look for the y-intercept, which is going to be here at negative 3. So we write minus 3. Write a second equation whose graph goes through 0, 2. So 0, 2. So the system has no solutions. What that means is we want to say so the lines never cross, they never intersect. So we're going to keep the same equation, or same slope, 1, 2, 3, up 2. I can go down 3 and over 2. Okay. If I graph that out, it looks something like this, right? So what we're saying is this would go on forever and ever, and because of parallel lines, it would never cross. So what is that equation going to look like? Well, it's y equals the same slope, 3 over 2x, and I look at my y-intercept, which is plus 2. Write a second equation whose graph goes through 2, 2, so that the system has one solution at 4, 3. Okay, so it's going to go through 2, 2, so here's 2, 2. It's going to go to that point there, and it has a solution at 4, 3. So 4 and 3, 1, 2, 3, so here. So we're looking for a graph that's going to go, in this case here, through that point to make that our solution. Remember, a solution with a system equation means the point at which they intersect where they cross. So I want to make an equation for that one right there. So in this case here, the way you can solve this a couple ways. Now one, I've graphed it, and by looking at the graph I can tell you what the equation is going to be, right? No problem, I can do that. But I also have 2 points. So because I have 2 points, I could figure it out that way, right? I know it has this point, and I know it has this point here. So to find the slope, first of all, for my slope, I do y2 minus y1 over x2 minus x1. It doesn't matter which one you want to use, it's okay. We can call this our y2, and we can call this our 1. So we can say 3 minus 2 over 4 minus 2, which equals 1 over 2. So my slope is going to be a half. So I know I have y equals 1/2 x, but I need to figure out that where it's across the y-intercept. So to figure that out, what I want to do is I can plug in any one of these values here to find out what this is going to be. We can write this as plus, and we're going to call this here, let's call it b. That's what it is. I'm going to do a capital B so you don't think it's a 6 for now. and we're going to plug in 2 and 2. So let's plug in the value of 2 there. So 2 equals 1/2 times 2 plus b. So 2 times 2, 2 times 1 is 2 over 2 is 1. So 2 equals 1 plus b. Subtract 1 from both sides, and 1 equals b. So what does that tell me? That tells me that my equation is going to be y equals 1/2 x plus 1. Now I can notice that that is the same point in my graph that it actually crosses the y-intercept, which is 1. I can also tell that I'm going, what am I doing? Up 1 over 2, up 1 over 2, and I can see the slope there with just the graph. So a couple ways of approaching that, you can decide which way works for you. That's it for today, and we'll see you next time.